You're about to learn how to quickly solve and understand this advanced integral problem that you might see from the JEE exam. So if you want to solve problems like these quickly on that exam or your AP exam in the future, you should click that subscribe button and let's get started. The first thing I want you to notice here is usually when you have a product of terms, one thing that comes to mind is, okay, can I use integration by parts here? And before jumping into it, I like to inspect the integral and find what parts look simpler, harder, and what parts also look really familiar. Looking at the secant squared of x term, to me personally, it looks like the simpler term to work with. But it also reminds me of the fact that secant squared of x is, in fact, the derivative of tangent of x, right? So going in the backwards direction then, if I were to use integration by parts here, I'm going to start by setting that as my dv term, because I know that if dv equals secant squared of x dx, then when you integrate both sides with respect to the variable, you get v equals tangent of x. And remember, with integration by parts, we have this remaining natural log of secant of x that we now have to deal with. And so we're going to assign that to this u term. Now, when you have u equals natural log of secant of x, this means then that taking the derivative of both sides, you'll get du equals, now remember, the derivative of natural log of x itself is 1 over x. But because we have secant here as the operand within the natural log of function, we have to remember to be careful here and use the chain rule. So the derivative of the natural log of secant of x would be the derivative of this outer function, which is a natural log function, giving you 1 over whatever's inside, which is secant of x, times the derivative of the inner function, which is secant of x. Now, you already might know off your memory what the derivative of secant of x is. And if that's the case, go ahead and feel free to skip forward. But for those who don't know how to find it, what you can use here is this property that, hey, secant of x is the same as 1 over cosine of x. And the reason why I'm going to write it this way is now that it's represented as a fraction, I can use the quotient rule. So we're going to assign the numerator of 1 to this variable u, and the denominator cosine of x to another variable v. And if you remember with the quotient rule of derivatives, what you're going to have is the derivative of u times v minus the other way around, right? So u times the derivative of v all over v squared. Now, the first term where you have the derivative of u times v, because u is 1, the derivative of that is simply going to be 0, right? So that term just will cancel out. And then minus, okay, you have u, the original u, which is 1, times the derivative of v. Well, the derivative of cosine of x is negative sine of x. And then this is all divided by cosine squared of x. And so when you simplify everything, you'll get sine of x over cosine squared of x. Now, this isn't wrong, but you still have a ratio here, right? And there's actually a simpler way of writing this. So I want you to remember that whenever you have something to a power, like cosine of squared of x, etc., there's nothing wrong with rewriting it like this. We can actually break this up as a product of fractions. We can say sine of x over cosine squared of x is the same as sine of x over cosine of x times 1 over cosine of x, right? And the reason why that's nifty is because we already have terms from trigonometry that we know for each of these. Sine over cosine is going to be tangent, and then 1 over cosine will be secant. What this means then is that since we did this extra work to figure out what u and du are in the original integration by part strategy, I'm going to go ahead and just, for simplicity, rewrite the original problem here with all the work that we did. So if you remember, dv is secant squared of x dx, and v will be tangent of x. Now, u equals natural log of secant of x, as we did before. And if you remember with the chain rule, the derivative of that's going to be 1 over secant of x times the derivative of secant of x, which we just proved above. So I'm going to bring that down here as that tangent of x, secant of x term. And of course, not forgetting the dx. And then when you simplify du, you're going to be left with tangent of x. How nifty is that, right? So now doing integration by parts, you've got uv, so natural log of secant of x times tangent of x minus v du. And I always put v in parentheses just to make sure that my minus signs and plus signs are distributed properly. So tangent of x will be your v times the integral of du, which will be tangent of x dx. So the right-hand side, we can distribute that minus tangent x through, and we're going to end up with this minus integral of tangent squared of x dx. Now remember, we can use an identity here. We know that tangent squared of x is the same as secant squared of x minus 1. And that's a really useful trick because if you remember just how we started out with the problem, working with the integral of secant squared of x is really easy because we know it's tangent of x. And more importantly, when you take the integral of something minus something, it's the same as breaking it up into two separate integrals and you subtract them, right? And so moving forward, we'll have natural log of the secant of x times tangent of x minus, now we distribute the minus through and we break this up into a sum of two integrals here.